Now in section 4.3, if we look at the objectives, there's only two on here that we're going to cover. Number 8 is find exact values of sine or cosine via a sketch and explain when a given theorem or identity happens. So this is really dealing with the theorems and identities. And number 9, find sine, cosine, or tangent in exact form using Pythagorean's identity. You are going to have to know how to do these two things. And we're going to break these notes into 2 days. So in this first day, I believe we're just going to cover 3 theorems, and then on day 2, we'll cover 2 more. So let's get started with that. Now this is section 4.3, so do fix this here. I should say 4.3. And we're going to cover 3 identities today, and then we'll do 2 more tomorrow in the notes. The first one deals with a Pythagorean theorem. So let's just look at this scenario here. They're saying if we draw an angle right there, in a unit circle, by the way, the radius is 1, but this is the radius, so I'll call that R. And to sketch that, though, you could drop a right triangle. We could move the right and the up movement. Well, in a right triangle, when we have the 2 legs, we can find the hypotenuse, or in this case, the radius. The 2 legs are the x value and the y value. Now, Pythagorean theorem states, remember, if we have a, b, and c, we would say a squared plus b squared equals c squared. But when we embed something in a unit circle, our a, b, and c changes. And let's just go one step at a time. First, we know our a and b in this triangle are the 2 red legs, so we're going to call them the x and y. So that'd be x squared plus y squared. And in this case, our c squared is our radius, or our radius squared. Now, in a unit circle, it's trigonometry. X isn't just x, it's cosine. So I'm going to replace x with the word cosine theta, and I'm going to square it. Y is sine theta, so sine theta and square it. And the radius in a unit circle is 1 squared. What happens is when you simplify this, here's what you get. This simplifies into cosine squared theta plus sine squared theta equals 1. And notice how I wrote it. This is how you write cosine squared. This is okay, but this is not considered simplified. Here's what you need to be careful. Never would you write cosine squared theta like this. You would not say cosine squared theta without the parentheses because it looks like you're squaring the theta or the angle. So that is just bad. Don't ever do that. This is okay, but this is really the best way to do it. And this is what we call the Pythagorean's identity. It's basically applying Pythagorean's theorem in the trigonometry world. So it's going from the geometry realm to the trigonometry realm. The reason we do it is we can actually use this formula to help us either find cosine or to find sine when we're given one but not the other. If I'm given cosine, I could plug that in and I could find sine. Conversely, if I'm given sine, I could plug that in and find cosine. And let me show you how to do an example with this because it gets a little long. Okay, before that example, just take a quick peek at this. By the way, which one of these 2 expressions really is correct and which 2 kind of match up with each other? Be careful, these 2 right here are the appropriate ways to write it as tangent squared. We typically would write the final answer in the version that A is written and not C, but B is not equivalent, so just be careful with that. All right, let me show you how we would use this. They're telling us in this problem that the sine of an angle is 0.6. What is the cosine? And this gets a little tricky, so this might take you a few examples to see it. How to interpret this? The sine of an angle is 0.6. So if I think of an angle movement, I know it's cosine and I know it's sine. They're telling me the sine is 0.6, so I'm going to actually do this. That is 0.6 in an ordered pair movement. I don't know the cosine. So that's actually what it's telling me, is this given information. Well, can I graph that? I kind of can. I can graph part of it. What I know is I know that the x movement, I'm not sure, but I know this is the y movement. So I know I have to go up 0.6 in a unit circle. So that'd be 1, 2, 3, 4, 5. Here's 0.6. What I don't know, though, is when I first draw the ordered pair, which way am I moving on the x-axis? Am I moving to the right or to the left? I'm not sure. Well, what I can do is this. If you move this over, you land here. So what I've just discovered is I could either be here or here. So I know this much. I don't know the cosine, but I know the sine. I don't know this cosine, but I know that sine. I want to find the cosine that goes with it. All you need to do is use the Pythagorean theorem. So Pythagorean theorem says this, or Pythagorean identity, cosine squared theta plus sine squared theta equals 1. Sine is 0.6, let's just plug it in. So 0.6 squared equals 1. 0.6 squared is going to be 0.36. To solve for this, I just want to subtract the 0.36 from both sides. So this says the cosine squared theta is equal to 0.64. To get cosine theta by itself, just take the square root of both sides. And what I get is that the cosine of theta is equal to 0.8. Now, what that tells me is I had to go over to the right 0.8. But why do I also have this value here? Because when you have a quadratic or something squared, it could be plus or minus. It may also be negative 0.8. This problem actually has two answers. I don't know which ordered pair that they're talking about. They would have to be more specific and tell me if they want me to give them the answer that's in quadrant 1, or if they want the answer that's in quadrant 2. Okay. But be careful when you use the Pythagorean identity, because this is cosine squared theta, when you take the square root, you always get two answers, and it will show up in the graph itself. Okay. This picture part is probably the harder component to understand at first. Just know this, take away from this example that when you are given sine or cosine and you need to find the other, just plug it into the Pythagorean identity every single time and back into the other one. And then what you could do is when you're done is actually take this ordered pair information and graph the two ordered pairs that we found here. Here's another example, but they're actually, instead of using decimals, they're using fractions. And here's a problem in math. If the problem is stated with fractions, they want the final answer in fractions. So don't change these to decimals because you will not get full credit. And let's just do the math part first. They've given me cosine and they want me to find sine. When I see that, I should say, okay, I'm going to use Pythagorean's identity. So I jot it down. Okay. And then I just plug in. I have cosine, so find 3/5 squared. I don't know sine. 3/5 squared, be careful, means repeat 3/5 twice. It's 3/5 times 3/5. Multiply fractions straight across. That's 9/25. Okay. Now to solve this equation and to get sine by itself, I'm going to subtract 9/25 from both sides. If it helps you, you can just make 1 a fraction by putting it over 1. Common denominator in this case would be 25, so it'll be 25 here, 25 there. So sine squared theta is 25 over 25 minus 9/25. That gives me sine squared theta. On fractions, subtract, so it's going to be 16/25. Simplify, get sine squared by itself by taking the square root of both sides. Can break this up by taking the square root of the 16 and then the square root of 25. So it's going to be 4/5. Be careful, it's plus or minus. Now, if I wanted to draw the scenario, I could easily do that. I'm going to do an ordered pair of cosine I know is 3/5. Sine is either going to be a positive 4/5 is one of the answers, or it's going to be 3/5 and negative 4/5. Okay. So to sketch that, the 3/5 is going to be about right here, and then my 4/5 is either going to be this or that. So these are the two ordered pairs, and if you look logically at the answers, they should make sense. Here I'm going right 3/5 and up 4/5. Here I'm going right 3/5 and down 4/5. So look at the angles that are created though. It creates either this angle here or it creates this angle here. They're really very similar angles. They just go in different directions. So they are the same angle, but they're in opposite directions. If I were to guess, maybe this was about 50 degrees. To get here, I would do negative 50 degrees because that's how you move backwards, or clockwise, I should say, on a circle would be the negative movement. So just notice the connection here on this problem also. Okay. This leads us to the second theorem of the third, and it's the opposites theorem. And we kind of touched on it on that last slide. We looked at two angles that were opposites of each other. And I want you to notice what happens to the sine and cosine. So let's just do this. If you were to get your calculator out, and I'll jot down a few of these answers. If you get the calculator out and do the sine of pi over 6 in radian mode, and the sine of negative pi over 6. Okay. And then let's do this. How about the cosine of 72 degrees in degree mode, and the cosine of negative 72 degrees. Let's see what we get for those answers, because these angles are just opposites of each other. Where opposite is just changing the direction. So take a moment with your calculator. Let's see what we get for those. Okay, what you should have gotten, this will give you a 0.5. This one will give you a negative 0.5. This cosine here will give you a 0.309. This cosine here will give you a 0.309. So what you're going to see, if you have two angles and they're opposites, you're always going to see this connection. The x values, or their cosines, are always going to be the same. The y values, or their sines, are always going to be the opposite. Okay. Let me just show you a quick sketch of one of these. 72 degrees, folks. It's rough, but there it is. That's 72 degrees. That's negative 72 because I'm going backwards. The cosine of that is the x movement. The cosine here has to be right for both cases. They both have the same cosine movement. Look at their sine movements. This goes up, this goes down. So you can tell that they're in opposite direction, and that's why it's the opposites theorem. So let me formally state the opposites theorem. What the opposites theorem says, if you have an angle here, I'm going to the picture. If you have an angle, let's just say maybe it's 120 to help us visualize it, and it's opposite angle, that'd be negative 120. What do we notice about the cosines? Here, to plot the cosine of the x movement, you have to go left. You have to go left for both, so their angles are the same. So the cosine of a negative angle is the same as the cosine of the original angle. Okay? The sine values, what you're going to find is, for this sine value, I have to go up, and for this one, I have to go down. So the sine of a negative angle, or the sine of negative 120, if I were to find that, I would take the negative of the sine of the original angle. Again, what I'm doing is I would say the sine of this angle is the down movement. So what I would do is take the sine of this angle, which is the up movement, and just make it negative. That's what that says to do. The tangent is the slope of the line. Are they equal or are they different? If they're equal, I would say the tangent of negative theta is equal to the tangent of theta. Is that true to say? Are their slopes the same? Do they both go uphill or both go downhill? This one goes downhill right here, left to right. This one goes uphill left to right, so they're opposite, so they're negative of each other. If I wanted to find the tangent of the negative angle, which is right here, how I would find it is I would take the tangent of the original angle, which is this guy right here, or that, and then I would put a negative in front of it to get the opposite of it. Let me show you an example of how you can do this without a calculator. Suppose the sine of some angle is 0.15. Evaluate without using a calculator. What is the sine of the negative angle? Well, the theorem says, the opposites theorem says the sine of the negative angle is going to be equal to the opposite of the original angle. And if you don't want to memorize that, because you don't have to, let me show you how to do this in a picture. Here's what I like to do every time. The sine of an angle is 0.15. So I'll do this. I'll say, okay, sine and cosine are ordered pairs. That's cosine, that's sine. Again, the sine of some angle is 0.15, so that is the y value. That's what I know. I can graph that picture, by the way. I don't know if I go right, and I don't know if I go left, but I do know I go up 0.15. It's not a lot, so I'm going to go over a little further. I go up about 0.15. Let me just say it's that. And I'm just estimating. This isn't a perfect picture. Well, maybe they wanted me to go to the left and up 0.15. Fine. Right there. So they're talking about either one of these two pictures. They're just mirror images of each other, by the way, over the y-axis, if you look at that. Okay, what you want to do here is I'm just going to pick one of them, because let's just say I'm talking this angle. And let's say maybe it's 20 degrees. So if the sine of, and I'm just making this up, 20 degrees. If the sine of 20 degrees is 0.15, here's the question. What's the sine of negative 20? Where's negative 20? Well, negative 20 is backwards. It's right here. That's negative 20. Well, the question is, what's the sine? They want to know this component. Well, folks, these two angles right here are mirror images of each other over the x-axis. So instead of going right and up, I'd go right and down. So therefore, to go down, I'd have to do a negative 0.15. That's what the theorem says. The theorem says the sine of the negative angle is take the opposite of the original angle. So the answer to this problem is negative 0.15. Now, on a quiz and on a test, you are going to be required to have to sketch the picture. So this is the sketch right here you want to do. The one thing I will tell you, it'll be more clear if they're talking about this angle here or this one here. Don't worry about which of the two scenarios, if they want this one or this one. Just pick one of them. And in this case, I picked this one, which was, and I assumed it was 20 degrees, and then I drew its negative image over here. The last theorem for today, it's the third of the fifth, is called the symmetry identities, and it's a half-turn theorem. If I move half of a turn, I'm going to move 180 degrees. So here's how it works. They're going to say take a particular theta, or angle movement, and they're going to move this right here. That's their angle movement. They want to add a half turn to that. So they come in and they add a full half turn to it. Where do they land? Right here. Their question is, what's the relationship between these two ordered pairs? This first ordered pair I had to go right and up to get. Okay. This next ordered pair I had to go left and then down to get. What you're going to notice is the two ordered pairs are exactly opposite of each other. That's what this shows you. This says the cosine of an angle and the sine of the angle. Notice what they did here? They just changed them to the opposites of everything. That's how the half-turn theorem works every single time. So let's state the half-turn theorem. What you're going to notice, and they're going to either have it in degree mode. This is the degree. This is the radian mode. I can either take an angle and add a piece, or I can take an angle and add 180 degrees to it. Those both mean the same thing. If I do that, notice the cosine values. The cosine of this angle is going to be the opposite of the original. The sine of the angle is going to be opposite of the original. The tangent, folks, it's the exact same line. These two are actually the same line because we just did a half turn. The tangent is exactly the same. If you didn't want to remember it, you could just do tangent, which is sine over cosine. So you take the sine value over that cosine value, which would make it a positive tangent. So good luck on this homework. It can be a little tricky. Give it a try. We'll finish the notes tomorrow.